Okay, so today I'm going to introduce a new type of attack on machine learning models that we call model inversion. I'll show how that attack can actually violate the genomic privacy of patients who are involved in what's called pharmacogenetic medicine. And then I'll talk about countermeasures in what, to the best of our knowledge, is the first end-to-end case study of privacy mechanisms in medicine, where on the one hand, we show that one particular countermeasure, differential privacy, can prevent this attack. But on the other end, patients who are dosed with these private models are at increased risk of adverse outcomes in this medical application. We'll conclude by saying that current methods for preventing this attack fail to properly strike a balance between privacy and utility. And this is actually a pretty big deal when the cost of being wrong or being inaccurate is really expensive, like in a sensitive medical application. Okay, so now we'll dive into the biggest word on the previous slide, pharmacogenetics. And this is an idea that's been taking hold in a lot of areas of medicine recently. And the basic idea is we're going to have a population data set that contains some variables for a large group of patients, some facts about their genomics and other parts of their background. We can give that data set to a bunch of professor types who then apply a bunch of fancy machine learning models to the population data set. And they're going to get a trained model from that. They can give this model to a doctor, and then when the doctor has a patient, he can take the patient's genotype and maybe some clinical variables that talk about their medical history, their demographics, things like that. Feed these variables to the model that the professor types had trained before, and as output from that, get some guidance that they can use to treat the patient. And today we're going to look at one particular application of pharmacogenetic medicine to warfarin dosing. Warfarin is a really popular anticoagulant drug. And an anticoagulant is basically just a type of medicine that inhibits blood clotting. So this can help with things like stroke and other related risks. And it turns out that warfarin is actually one of the oldest and most well-studied applications of pharmacogenetics around. There are already over 100 articles and more appear each year. And the reason for this is that warfarin is actually really difficult to prescribe doses for. There's a really fine line that doctors walk, and if they don't prescribe enough, then some really bad things can happen, and the same goes if they prescribe too much. And on both ends of this, there's this really ugly eventuality of the patient dying because of the treatment that they're undergoing. This also explains warfarin's original use, which is as a really potent rat poison, as a matter of fact. So we're going to look at one particular warfarin dosing model that was developed by the International Warfarin Pharmacogenetics Consortium, or the IWPC, which is much easier to say. And a few years back, the IWPC did a really big study where they collected data from about 5,700 patients from 21 hospitals in 6 countries from all around the world. And the sorts of things that they collected from each patient were, say, their basic demographics, some relevant parts of their medical history, 2 aspects of their genotype that researchers had previously found affect warfarin metabolism, and an outcome variable, which describes the stable dosage of warfarin that achieved optimal therapeutic benefit for that patient. The IWPC scratched their head over this data for a while, and they concluded that ordinary linear regression, a really simple type of machine learning, worked best in this situation. So they basically got a model that takes as input the patient's demographics, their parts of their medical history, and their genotype. As an output, it predicts a good starting dose of warfarin for their anticoagulation therapy. And up here is an excerpt of the actual model that the IWPC published. Some doctors actually use this today to prescribe warfarin. And if we go back to our pharmacogenetics flowchart, we see the genotype, or those 2 alleles that I showed you on the previous slide. And the clinical variables are the things like the demographics and the parts of the medical history. The pharmacogenetic model is exactly this linear expression, right? So a doctor can do this with pencil and paper or use a computer to evaluate it really quickly. And the guidance that this is providing is a good starting initial dose of warfarin. So when we first started studying this problem, we're concerned about the threat that this might pose to the genotype of the patients who took part in this study. And in previous work, people have looked at things like a situation where an adversary is given one or more data sets. Maybe some of them are anonymized, maybe some of them aren't. And then maybe some facts about some of the patients in that data set. And they can do, sort of a linkage attack and figure out some sensitive variables. In this case, the genotype is what we're concerned about today. We're looking at a different type of scenario. It's actually not all that common for these researchers to publish an entire data set. It contains a lot of sensitive information, so you can't get a hold of that very often. What is more common is for researchers to publish the models that they derive from those data sets. And this is actually really common practice in the medical community. So we assume that an adversary has access to that pharmacogenetic model, and then the output that would provide for a patient. You could imagine somebody getting this by maybe asking how much medicine someone takes or looking in their bathroom cabinet. In addition to some basic demographic facts about a particular individual whose privacy they're trying to violate. And the idea in our attack is the adversary is going to use all this information about the patient to kind of run the model backwards and predict that sensitive genotype. And this is what we call model inversion. Okay, so now let's see how this attack actually works and how we apply that to violating genomic privacy. So in model inversion, we're looking at a situation where an adversary has some specific information about one particular individual. So we assume they have their basic demographics, their stable dosage of warfarin, and we also give the adversary black box access to the pharmacogenetic model in question here, so they can pose input-output sorts of queries to it. We also assume that the adversary has marginal priors on the distribution from which this patient was drawn and over which the model was trained. And just to give you an idea of what these priors look like, this is the prior for one of the genotypes that we studied, VKORC1. It's basically just a breakdown of the probability that this variable can take different values. And so we assume the adversary has these priors for every variable in the data set, and this is reasonable because doctors or researchers commonly publish these priors alongside their models so that other researchers kind of have an idea of what the population they studied looks like. And of course, the adversary's goal is to infer the patient's genotype from all this information that we've given them, and hopefully to do so with better accuracy than they could get just by guessing from those marginal priors, so without access to the model. So we designed a general algorithm for doing this in the black box setting, and I'll sort of walk you through how it works at a really high level, kind of from 10,000 feet, just so you can get an idea of the kinds of principles that it works from. So first of all, the adversary is going to compute all the values for the missing variables that he doesn't know that could possibly agree with the facts that he has been given. In our setting, I said that the adversary has access to the patient's demographics and their warfarin dose, but not their medical history or their genotype. So the first step is the adversary just fills in all the possible configurations for these unknowns that could agree with what he's already seen. He then sort of runs the model forward on each hypothetical patient in this data set and sees what the model would predict for a stable warfarin dosage. And already this kind of gives him some notion of how well the values that he's guessed agree with the data that the model was trained on. He then goes through all the possible configurations and does a kind of likelihood computation to see which configuration is going to be the most probable. And he just picks the one that actually has the highest likelihood. So I won't go into the details of how this likelihood computation works. We write about it pretty extensively in the paper, and you should consult that. But more or less, he can do this using those marginal priors and the output of the model, because that sort of gives some joint probability information on that underlying distribution. We'll say that we argue in the paper that the algorithm we have for computing these likelihoods is optimal given the information in the model inversion setting, in the sense that it minimizes the adversary's expected misprediction rate for these missing genotypes. So let's see how this does on the IWPC model. And here we'll just look at one of the genotypes, VKRC1, and we measure this relative to a baseline where the adversary doesn't have access to the pharmacogenetic model. So he's just guessing based on the priors. And all here refers to a situation where the adversary has access to everything but the genotypes he's trying to predict, whereas basic means he just has access to the patient's basic demographics. And already we see that there is a privacy threat here. The adversary has a pretty huge advantage over the setting where he doesn't have access to the model. But if you're not convinced by the 20% or so advantage, if we look at this from a slightly different perspective, where we're comparing against a setting where we take the original raw data set, the same data set the AWPC model was trained on, and then train a linear regression model to predict that specific genotype, VKRC1, we see that model inversion doesn't do that much worse than sort of the best possible you could do trying to predict that from the data that was available at the time of training. And so this is why we think that this attack works in this setting, right? It doesn't do that much worse than you could possibly do trying to predict a patient's genotype from the correlated variables in the population data set. Okay, so now we'll talk about countermeasures and this end-to-end study that evaluates how well we can actually do preventing this attack. So I've shown that model inversion is a problem. How can we actually prevent it? We looked at the use of differential privacy for this. And recall, we say that a computation is differentially private if any output that it produces is going to be about as likely, regardless of whether or not any particular individual row is in the input to that computation. And this is an attractive way to do privacy, because when we state that definition formally, this allows us to make some really clean, provable guarantees about how we're protecting the input to a computation. But why would we necessarily think that differential privacy can help with model inversion, right? This definition doesn't say anything about protecting attributes or genotypes or anything like that. Well, it turns out that most differentially private mechanisms work by adding noise to their output in some capacity. And the amount of noise that they add is dictated by what's called a privacy budget. And there is some existing work that shows in sort of a similar setting to this that the attributes over which linear models are trained can be protected by adding noise to the coefficients of those linear models. So for us, the question is, can we find a reasonable privacy budget that allows us to add just enough noise to the model to protect these genomic inputs without sort of overwhelming the model with so much noise that it gives us garbage outputs? And this is what the end-to-end study characterizes. So on the one end, we're going to find a range of privacy budgets that does prevent our model inversion attack here. And on the other, we're going to evaluate how well pharmacogenetic models that are trained at those privacy budget settings do in predicting warfarin dosages for patients. To do the first part of this study, we looked at two differentially private mechanisms that at the time we did the work were sort of the best in class for either private linear regression or private histograms. And we actually do the experiments just by replicating the methodology that we used when we looked at model inversion for the IWPC model and subbing in differentially private versions, wherever we have to access the model. And I'll show you what the results for that look like in a minute. But first, I want to explain how we did the second part of this end-to-end study, evaluating how well these models actually work, in sort of a clinical setting. To do this, we actually simulated warfarin clinical trials as they've been done, in the physical world in the past. And what these clinical trial simulations look like is we start out by enrolling a patient, and for us this means sampling a row from the IWPC data set, their validation set. So the model wasn't trained over any of the patients we're evaluating here. We then prescribe that patient an initial dose of warfarin, and we can do this in one of two ways. We can assign them a fixed dose, 10 milligrams for the first 2 days. This is how doctors actually do this in real hospitals. Or we can assign a dose that's recommended by one of these private models. For the remainder of their trial, we then measure the patient's physiological responses to the doses that we've prescribed. And this is pretty complicated, but there's a really good literature in the medical community here called PK/PD modeling, and we make extensive use of that. And then based on these measurements, we modify the amount of warfarin that we're giving to the patient based on what we've already seen. And there's sort of a paper and pencil way to do this. It's very deterministic. That's actually been used in physical warfarin trials in the past. So let's take a look at the results for our end-to-end study. And first we'll look at how a model inversion does on differentially private linear regression at several different privacy budget levels. For those who aren't too familiar with differential privacy, epsilon is the variable that characterizes this, and small values of epsilon mean more privacy, large values mean less privacy. And in the paper, we concluded that epsilon less than or equal to 1 actually doesn't give the adversary that much advantage over this setting where he doesn't have access to a pharmacogenetic model, so we call that the good range. And when we superimpose the curve that we got from these simulated clinical trials, which measures the relative risk of mortality, and this is taken relative to the fixed dose protocol that doctors actually use these days, we see that these private models aren't actually a good solution. In that good range, even at epsilon equals 1, we're still a significantly higher risk of mortality for the patient, about 1.2 times as much as those fixed dose models would allow. And it turns out the private models aren't even close, because at epsilon equals 5, there's still a statistically significant increase in the likelihood of this negative outcome. So we're not exactly saying that privacy leads to death. What we are saying is that we didn't observe a single range of privacy budgets that is effective at preventing model inversion without introducing all sorts of increased negative outcomes for the patients over the sort of private by default fixed dose way of prescribing warfarin. Okay, the session chair is telling me that I'm out of time. 1 minute. Yeah, so I'll leave it there and take questions.
All right, thanks, excellent presentation. If you have a question, please come up to the mic, state your name, affiliation, and astrological sign.
Okay. Murat Kantarcıoğlu, University of Texas at Dallas. My question is, first of all, in one of the data sets, one of the genes, you didn't get a good result. So I wonder whether the prior information was too strong or you don't see model inversion attacks compared to a good prior information. So if the attacker knows lots of stuff, the model is kind of equivalent to model type of scenario. And the second thing I was going to ask is, when you look into differential privacy, there are many other models. So why you chose two and why didn't you compare with others? So is it more generic?
Right. So your first question was, it sounds like you read the paper and you saw that the other genotype, so the genotype that we didn't show results for in this talk it actually has a really funny distribution. It's very skewed. So one of the alleles is very, very probable, like 75% of the population has it. And the other 5 alleles, the other 5 possible values, just share a tiny sliver of the mass of the distribution. And so sort of you can get 75% accuracy just by guessing that one allele that 75% of the population has, and model inversion doesn't do much better than this. We do talk at, I think we have a few paragraphs in the paper as to why this might be, but it seems to be that this variable, because it's so skewed, doesn't actually change the outcome of the model that much. It gives a slight increase in accuracy, and so going backwards on that, you can't do much better than just guessing the sort of baseline most likely value most of the time. What was your second question? Oh. So there are a lot of differentially private mechanisms. We studied 2. It's because they sort of match linear regression, which is how the warfarin dosing models work. It's by no means conclusive in that sense, and we'd love to try the study on lots of new models as they come out.
Ben Lashitz, MSR. So it sounds like you've interacted with doctors and medical researchers quite a bit in conducting this research. So what is their attitude towards privacy, in particular the kind of privacy in the sense that you talk about essentially?
So one of our co-authors is a doctor, and his attitude towards privacy might be a little skewed. He's on this NIH grant with us that specifically looks at privacy in these genomic applications. He seems to recognize that it's a valuable thing. When it came to differential privacy, I believe when we first explained it to him, he was a little disturbed by the idea of just adding random noise to these medical decisions that could have dire consequences for patients. As for the rest of the medical community, I don't know. Your guess is as good as mine.
And I'm sorry, we only have time for one more question, so last question.
Okay. Rachel Greenstadt, Drexel University. I was wondering, did you compare your model inversion on the initial dose to perhaps doing it on the modified dose? Because I know that warfarin is highly variable to a number of different things that cause the modified dose to have a lot of noise in it anyway. So like diet and how much green leafy vegetables people eat and so on. So.
Yeah, so in our experiments, we didn't assume that we knew the initial dose. That would, if the initial dose were predicted by the model, that would make the inversion problem pretty trivial. It's just solving so we only looked at the one setting where we know the eventual dose that was settled on after titrating for some time, and the other scenario is, as I said, like trivial to back out the the inputs.
Interesting, so it's still very deterministic.
Yeah. Yep.
Right, let's give Matt a big round of applause.